Good morning. Perfect. So first I will start with a little bit of background, then I will move to the algorithm, some results, and the conclusions. So as we've seen these days, GC by GC is a commonly applied technique in volatilomics and in the analysis of highly complex matrices. When coupled to high-resolution mass spectrometry, it provides improved chromatographic resolution, increased peak capacity, and enhanced sensitivity, enabling more reliable feature detection and annotation. These capabilities have led the widespread of the adoption of GC by GC in multiple application domains, including forensic chemistry, environmental analysis, petrochemical and fuel characterization, food, flavor, and fragrances, and as well in biological applications, such as metabolomics and bulk profiling. In particular, GC by GC has demonstrated exceptional performance for the characterization of complex biological matrices, such as urine, human plasma, and also for breath. However, as this technique is improving and also the instrumentation is evolving, the complexity of the data is also increasing. A single GC by GC experiment generates a third-order data tensor, comprising the first dimension retention time, the second dimension retention time, and the spectra associated. Consequently, when we are analyzing multiple samples together, we are obtaining high complex data sets that are four-dimensional. This complexity can be also beneficial, as it allows us the use of advanced data analysis tools that take the full advantage of the high-order tensor structures. At the same time, this complexity represents a significant barrier for new users, as the effectively data handling and interpretation requires high level of technical and chemometric expertise. The data must be transformed into chemical and meaningful information through dedicated data processing pipelines. In practice, these steps are often performed using commercial softwares. However, some researchers find that these softwares are not customizable, so they find some problems to automate all the processes. For this, we present GcDUO, which is an open source software tool for processing GC by GCMS data, enable feature identification, deconvolution, and analysis. GcDUO processes the raw data to extract the features without any prior knowledge of the samples, and then performs the convolution and the identification. It's implemented in R, available at GitHub, and is designed for untargeted and batch analysis. GcDUO comprises 6 modules that I will detail now. Modules 1 to 3 are integrated into a single function, where the first step involves reading the raw files. It uses standard CDF files, which are non-vendor specific files. The fields contain data vectors, which are folded using the modulator parameters into the 4D matrices. Here, the user only needs to put the path for the files and the modulation parameter. When we have the 4D object, we aim to select the region of interest, or ROIS, where we will deconvolute our data. To achieve this, we use the inverse watershed algorithm. This algorithm evaluates the data to identify prominent points and then defines the volume. Before moving to the next step, the ROIs are assessed based on the peak shape and the signal-to-noise ratio, that also is a parameter that the user can choose. Once we have the ROIs, we proceed to extract the relevant information. We apply the parallel factor analysis algorithm, PARAFAC, to each sample and region individually, as well as iteratively. PARAFAC is a tensor rank decomposition method that has been successfully applied to GcDUO data for the convolution, noise reduction, and calibration previously. Based on alternating least squares decomposition, PARAFAC requires at least three-way data, which necessitates to be trilinear. It decomposes the data into three small parts. We will have, in our case, the two chromatographic profiles and the spectra for each component extracted. This step is performed iteratively, as PARAFAC needs to know the number of components. So we are performing the model, increasing the number of components until this is not improving. After obtaining the necessary information, the feature coordinates and the spectra is retained. We check the consistency between samples and duplicates are removed. With this information, we obtain the features, and a consensus spectrum is created based on the exact retention times of both dimensions and the maximum mass-to-charge fragment. This consensus spectrum is then matched against the library using the dot product or the cosinus similarity. So users can import their libraries if they have in MS format. Optionally, retention index can also be incorporated to the matching process to help in the identification. So from here, this is more or less the typical pipeline that we find in all the softwares, but we added an extra step, which is the refinement. Although we have obtained features with tentative identifications, the information is not accurate enough. The PARAFAC model can enhance the results when we introduce as many parameters as possible. So what we do now is perform again the model, but giving the PARAFAC all the information that we obtained previously. So what do? We use the 4D matrix. So we use all samples together now, which enables the batch processing. Then we define the exact time windows that we have obtained, and also the number of components that we want to extract. This way, the model provides more precise results and also allow us to find peaks that are small or not well resolved. From these results, we calculate the peak areas using the area under the curve. As we are using now batch samples, we select PARAFAC2, which is a modification of PARAFAC that accommodates the loss of trilinearity in the data. So we have batch samples, and this is a common thing that happens when we are analyzing in batch mode. So now we will move to the results. To illustrate the functionalities and results of GcDUO, we use three datasets. The first one is the training dataset, which consists of a mixture of 36 compounds at increasing concentrations. This allows us to compare the results across both low and high intensity signals. The first part that we check is that we are detecting the ROIs correctly, that are the regions suitable for the deconvolution. The training dataset is segmented into windows, encompassing all samples while preserving the 4D structure. In the figure, we observe one window in unfolded format for graphical purposes. As a result, the inverse watershed algorithm identifies the prominent points in our tick, which is the pink line at the bottom, and select the areas to deconvolute that are in green. Once the ROI are established, peak characteristics are assessed. Only peaks with adequate signal-to-noise ratio and a Gaussian shape are retained, as the ones shown here. To illustrate the PARAFAC performance, we select 1,8 cineol, a peak that overlaps with limonen in our training dataset. Although a good chromatographic shape is observed, for the spectra, after applying PARAFAC, this is not ideal for identification. So this is the spectra up here, and this is a quite clean matrix. So if we have more complex matrices, this will be worse. What we see is that we apply the PARAFAC constrained, the spectra improves, which is the result here, increasing the similarity between the sample and the library spectra. Then we also check the differences between PARAFAC and PARAFAC2. The additional information provided to the model enables precise results. Despite both of them are similar, we see that PARAFAC forces the alignment of the peaks that might cause an over or underestimation of some areas that we are obtaining. If we are using PARAFAC2, the original data is maintaining the area of the compounds. Now we move to the validation dataset. First is the Fruity Beer, a public dataset of 5 beer aromas, comprising a total of 27 compounds. The annotation of the compounds was tested. A total of 85% of the peaks reported by the authors were successfully annotated using GcDUO. From the peaks that were not detected, one was missing from our in-house library, and the undetected peaks correspond to a small chromatographic signal with few fragments to the convolute. So PARAFAC fails when you have spectra with too few fragments. Then we test the breath mix, which is a mixture of 12 compounds, characteristics of breath. For this, we successfully identify all the compounds. We have to say that one compound was only detected when one lowered the signal-to-noise ratio. So this is a thing that we can do, but this introduces a lot of spurious peaks. We also observe that when we use PARAFAC, there is a degree of noise reduction in our data. So from all of the results, the only thing that we have done is PARAFAC, and we are presenting the results. As we see in blue, is the line obtained after PARAFAC, and this is approaching to 0. This helps in the noise reduction and avoids more steps in all the processing. From the breath mix dataset, we could compare the area obtained with the vendor software Chromatograph. Retention time were consistent between both softwares, and additionally, the peak areas show a Pearson correlation of 0.9 between both softwares. These results highlight the suitability of GcDUO for analyzing GcDUO data. So, as a wrap-up, GcDUO addresses the challenges of raw GC data analysis by providing a comprehensive suite of tools for processing, the convolution, and interpretation. Implemented in R, the software operates through several key modules that each one can adapt as they need. It accepts non-vendor specific files and rearranges the data into 4-dimensional tensor structures, preserving the GcDUO data integrity in every dataset. GcDUO uses advanced chemometric techniques, including parallel factor analysis and its variant PARAFAC2. Despite the advantages, GcDUO has some limitations, such as the high computational cost, which restricts the use with low-resolution data. Additionally, PARAFAC assumes the linearity of the dataset, making a preliminary inspection of the raw data essential. GcDUO offers a tailored platform for GC studies using advanced algorithms to enhance data reliability and reproducibility. So now it's on GitHub, and we will be happy if all of you can try it and say what problems can occur. So thanks for your attention, and I will be happy to answer questions.